When the electric grid goes dark, the water in a city does not instantly disappear. The real question is how long operators can preserve pressure before stored water, backup power, and fuel begin to run out. A city blackout creates an unusual split screen. Streetlights, elevators, and traffic signals may stop immediately, while drinking water can continue to arrive as if nothing happened. That delay is not evidence that the water network is independent of electricity. It means the network has stored energy in several forms. Water already sits inside reservoirs, tanks, and pipes. Elevated storage converts height into pressure. Pumps that were running before the outage may have filled those tanks near their normal operating level. The network can spend that reserve for a while, but it cannot replenish every part of the system without power. The central problem is pressure. A utility does not merely need water somewhere inside its network. It needs enough controlled pressure to move water through treatment processes, across long distances, uphill into pressure zones, and finally through the service line at each building. Pressure also helps protect water quality. If pressure falls too far, leaks and damaged joints can become pathways through which surrounding material enters a pipe. That is one reason an outage may eventually lead to isolation, flushing, sampling, or a boil water advisory even after electricity returns. Gravity can do important work. A high tank can keep feeding lower neighborhoods without an operating pump, and a full service reservoir can smooth a short interruption. Yet geography decides who benefits. A low district near storage may retain service, while a high district dependent on a booster station loses it much sooner. Operators therefore begin with a map of dependencies: which sources require pumping, which treatment stages need electricity, which tanks can feed which zones, and which stations have reliable backup. A blackout does not create one citywide countdown. It creates several local countdowns, each set by storage level, elevation, demand, pipe connections, and the power available at critical equipment. The first seconds of a blackout are handled by electrical protection and control equipment. At a critical facility, a transfer switch detects the loss of utility power and separates the site from the grid before connecting an on-site source. That separation matters because a generator must not feed electricity back into lines that crews may be repairing. An automatic transfer switch can restore selected loads at an unmanned station, while a manual connection may be acceptable where an operator can arrive before service is threatened. Either choice is part of an operating plan, not simply a piece of hardware. A generator must be sized for the loads it will actually start and run. Large motors can demand more current during startup than during normal operation, so nameplate running power alone does not describe the whole job. Utilities identify essential loads: controls, communications, disinfection, source pumps, treatment equipment, and the distribution pumps required to protect priority pressure zones. Non-essential equipment may remain off so limited generation can support the parts of the process that keep water safe and moving. The generator is only one link. It needs a working starter, cooling, ventilation, a compatible connection, tested switchgear, and fuel. A portable unit also needs a prepared pad or connection point, the correct cables, transport, trained staff, and safe access during the same storm or emergency that disrupted the grid. EPA guidance emphasizes planning these details in advance because a generator that exists but cannot be connected, refueled, or reached is not useful resilience. Flood risk complicates the plan. Electrical equipment and fuel systems have to remain protected when the outage is caused by water around the facility. Control systems give operators a wider view. Supervisory control and data acquisition, usually called SCADA, can report tank levels, pump status, pressure, alarms, and transfer switch activity. But communications may have their own dependencies, so utilities also prepare for lost telemetry and manual checks. Operators use the information they still have to decide which pumps run, when tanks are refilled, and which zones receive priority. Hospitals, emergency shelters, firefighting requirements, and facilities that cannot easily reduce demand can influence those decisions. Demand management is another form of backup. Asking customers to limit irrigation and other discretionary use slows the fall of storage. Pressure can be adjusted carefully, and interconnections may provide an alternate route where neighboring systems and water quality rules allow it. Mobile generators, mutual aid agreements, spare parts, and fuel contracts extend the options, but they are constrained by the same regional emergency. If roads are blocked or every utility calls the same supplier, a plan based on immediate delivery may fail. The strongest system therefore layers defenses: gravity storage for an instant response, permanent generation at the most critical sites, portable connections elsewhere, multiple fuel and equipment arrangements, communications, trained crews, and a documented minimum level of service. Redundancy is not one oversized machine. It is a chain in which the electrical, hydraulic, logistical, and human links have all been tested together. Even a well-prepared network can reach the point where backup becomes triage. Fuel may be conserved for the stations that protect the largest population or the most vulnerable pressure zone. A pump can be available while its upstream source is not. A treatment plant may have electricity but lack a chemical delivery, a working communications link, or enough staff to operate normally. Operators may isolate damaged areas, move water by another route, or issue restrictions that trade convenience for additional hours of pressure. The consequences are not limited to the moment power returns. Tanks that drain during an outage must be refilled, pressure has to stabilize, and parts of the system may require flushing, sampling, or disinfection. Water that remained in storage or low-flow zones can age, changing the water quality problem even where some supply continued. Recovery is therefore a hydraulic and public health process, not an electrical switch flipped back to normal. Research on the potable water systems of St. Thomas, St. John, and St. Croix illustrates why local topology matters. Researchers simulated different pump station outage scenarios and found that systems with superficially similar components could lose service in different regions and at different rates. Storage extended service in some scenarios, yet refilling tanks could take much longer than the initial restoration of delivery. The useful lesson is not a universal number of blackout hours. It is that utilities need to model which powered components control each service area, because the most valuable generator location in one network may be the wrong priority in another. This is also why routine tests matter. Starting a generator with no load proves less than transferring the real critical loads, observing pump startup, checking communications, and measuring how the hydraulic system responds. Exercises expose incompatible connectors, stale contact lists, fuel assumptions, and equipment that cannot carry the planned load. The city that keeps water flowing is not relying on luck or on one dramatic backup generator. It is using storage to buy time, controls to see the problem, operators to ration limited capability, and rehearsed logistics to keep the electrical and hydraulic chains connected. When those layers work, the tap can remain ordinary during an extraordinary event. When they fail, the first warning may not be an empty pipe. It may be a falling tank, a low-pressure alarm, or an operator deciding which part of the city has to wait. The next time a blackout leaves the tap running, remember what you are seeing: stored elevation, isolated electrical systems, fuel, communications, and operators spending a limited reserve of time. The most resilient networks know exactly which link fails next and have already practiced what to do about it. Beneath the network follows those hidden chains through the systems that keep ordinary life working. Subscribe for the next investigation, and tell us which piece of city infrastructure you want traced from failure to recovery.